So welcome back after this stimulating coffee break. Now it's time for Aharony's third lecture. So please, Amnon, go ahead.
Thank you. So my plan for today's lecture has three parts. The first part is a debt that I owe you since my first lecture. I was strongly attacked about the critical behavior of compressible systems, so I will say a few words about that. And then I'll come back to the where I stopped last time about NC and what is it and what are the implications of it having a value larger than 3 or smaller than 3. And then if I have time, I'll spend some time on fluctuation-driven first-order transitions. So far, I discussed only strontium titanate and lanthanum aluminate, but rubidium calcium fluoride is also a perovskite which is similar to strontium titanate. It has a first-order transition, and it turned out that Miller and then Bruce and I worked on the rubidium calcium fluoride, and there were interesting results also there. So the legend of the perovskites continued beyond the point where I stopped last time. So here are two papers on the compressible lattice. They were both published in the Physical Review B in March '76. One was by Bergman and Halperin, and the other one was by De Maura, Lubensky, Imri, and myself. I apologize for re-showing you all the time papers that I wrote, but that's life. I didn't even remember this paper when the question arose 2 days ago. So what Bergman and Halperin did, and their paper was much more detailed than the second paper I just mentioned, they introduced the coupling to the elastic degrees of freedom. Indeed, under Fourier transform, as Martin predicted and as Slava predicted, on Fourier transform, the derivative of the displacement by the location generates a Q factor. So there are extra factors of Q all over the place, and that generates terms in the Hamiltonian, which involves Q times U times psi times psi. Psi is the order parameter, and then there is a more complicated quadratic form for these U sub Q Fourier transforms of the displacement. And what they find is that the phase transition at constant pressure must be at least weakly first order. And then if the crystal structure can be, if this crystal fracture can be avoided, then there is another critical point with Fisher normalized exponents. I have no time to get into that, but I will say something about that later. And by contrast, the anisotropic cubic solid will develop a microscopic instability so that TC cannot be reached regardless of boundary conditions. So the results of compressibility of the crystal depends on the boundary conditions. Do you pin them so that they cannot move, or are they free? And the compressibility does affect the details of the phase transition, but then they say, as was pointed out by Rice, Domb, and Pipard, and later by many others, this question is of particular importance if the specific heat of the ideal system diverges at TC, as it does for the Ising model. So compressibility is important for the Ising model because the specific heat exponent alpha is positive there. The elastic degrees of freedom couple like an energy term, and as you already heard many times during this week, energy coupling is stable or unstable depending on the question, is alpha positive and negative. Our paper on the same topic started the same way with the Q-dependent parts, but unlike Bergman and Halperin, who actually solved the full problem of both the order parameter and the elastic degrees of freedom, we integrated over the elastic degrees of freedom, generated an effective Hamiltonian only with the order parameter degrees of freedom, alas with Q-dependent coefficients. So for example, there is a quartic term with a coefficient which is not a constant like I had in all my previous discussions, but it depends on Q. And however, we still say at the end that we close with the observation that in practice it may be very difficult to see any evidence of the anisotropic runaway discussed here. This is because the crossover exponent is equal to alpha, which is always quite small. So this is a whole topic that many people worked on around 1976, and people can read about it there. In practice, I don't think that to date there has been any evidence experimentally that these terms coming from the fluctuations in the elastic degrees of freedom can be actually observed and can affect the details of phase transition. So for our purposes, today we'll stay with the theory I described 2 days ago and ignore these fluctuations. So now I'm back to NC. Why is it important? So there are several questions here. What are the theoretical exponents for the fully cubic systems? Is it dominated by the Heisenberg or by the cubic fixed point? And how do the bicritical, tetracritical phase diagrams look like? How are they affected if n is larger than NC or smaller than NC? And in particular, what is the universality class of the perovskites? Remember, I started with a picture of experiments from Mueller showing both lanthanum aluminate and strontium titanate on the same diagram, showing apparent universality. Are they really universal? So this was a review by Roger Cowley in 1996. That's already 20-some years after the beginning of this history. And then he says, the theoretical situation of the cubic n equals 3, d equals 3 system is also somewhat uncertain, he said in 1996. And then he cites me and cites the others who said whatever. And he says that it was apparent during the 20 years before 96 that the exponents should be Heisenberg exponents, beta 0.365, gamma 1.386, a new 0.705. He took that from Leguieu and Singer-Stan. Since then, as I will show in a moment, there were many more accurate even calculations of the Heisenberg exponents. This is what is expected. However, he also mentions papers by Bruce and Natterman, on which I will mention in the last part of today's talk. However, he ends up saying that after developing the mean field theory of phase transition, the next step is to understanding the critical phenomena, although this has not been established for strontium titanate. And my punchline today will be that, I'm sorry, it has not been accomplished even today. Okay. So here is a paper, this is a paper from 1999. I think it was published in it was published in 2000, a 6-loop expansion, epsilon expansion for the n component Ginzburg-Landau Hamiltonian with cubic anisotropy. And here these guys summarize the previous history. I don't know if any of these people are present in the audience, they may be. Anyway, their conclusion from they give the history here. I think this is my paper saying 3.1 for NC. Remember, I padded a 3-term epsilon expansion for NC. And then they have all these other history of this. There were epsilon to the 5, and then there were these epsilon, this work is these people's work, and they conclude that NC is 2.87 or 2.89. It's below 3, which means that at n equals 3, the result depends on the cubic fixed point. However, look at the omegas. Omegas are the stability exponents for the Heisenberg and cubic fixed points. They are very, very small. So we are very close to being stable or unstable.
There appears to be a comment on the chat about this, if I understand it correctly. Maybe Kai will say something.
The table, you mean?
On the chat.
So there are 6 loop calculations from the Epsilon expansion in 2019, and they say NC equals 2.915 with an uncertainty of 3 on the last digit.
Yeah, I will show more papers. So if you bear with me, maybe you comment after I finish this story. Okay.
But just we are now at the most precise, hopefully most precise value. So there is something which is better than what you cite here.
Finish the review, and if you will have anything to add, I will be very happy.
Let's go on with the review, please.
Yeah. So here is a paper from 2002 by Pellicetto and Vicari. These guys have been very, very active in calculating critical exponents all along, and they also review the history and they review NC. And as you see, there is the values they cite, except for my value from 1974. Many of the values they cite are below 3. However, there is here one which is near 3. Otherwise, the conclusions of these guys is also that NC is below 3. Here is a paper by people, I think maybe all of these guys are present in the audience, and this is a Bootstat paper in which they say they use a numerical conformal bootstrap, and they conclude with a numerical proof that systems described by the cubic O3 system are unstable to cubic anisotropy. And we saw this slide last week from these papers, and this is a bootstrap picture, which I cannot explain. However, this was from David Polland talk, and he concluded critical Heisenberg magnets are unstable to cubic anisotropy. Okay. Here is a 5-loop renormalization group expansion in the Epsilon expansion from Kleinert and Schulte-Freunde. From doing Padé expansions, they got this result for NC, and they concluded from several Padés that NC apparently is close to 3, but below 3. And then he took, this was I think this was, I cannot see the upper part because of the zoom, but I think three years later came this paper. This is from I think this was from 2019. You guys can see the top, I cannot. From this group, 6th order epsilon expansion. And as you see, they give many, many references to earlier work. And then they said that earlier people thought that NC is larger than 3. And then they said maybe it's practically equal to 3. And then they went on to say that the various more recent references that they give conclude 2.85, 2.87, 2.91, 2.86, etc. This is their own expansion. Here is their epsilon expansion for NC. You obtain NC by either equating the cubic and the Heisenberg fixed point, namely you take the critical value of V, which is non-zero for the cubic fixed point, and you equate it to 0, and then solve for n, and you get n as function of d. or you can at the same time also require that the stability exponent of both the Heisenberg and the cubic fixed points at this n are all zero, because the two fixed points coincide, and that gives the same expansion for NC. And then they did Padé, and they did Padé, Borel, Leroy, and so on. And from all these Padé, Borel extrapolations, they conclude 2.915 plus or minus 0.003. And this seems to be the latest statement of the community on this issue.
Can I ask a question?
Yes.
So all these higher loop studies, they presumably compute not just NC, but they compute also the couplings at the fixed point.
They do, yes, and they find them to be very small, very close.
Yeah. But yeah, so my question was, do you know if it is still true? You know, in low orders, we know that the cubic fixed point lives at positive V when it's stable and at negative V when it's unstable.
Correct. I think that's what they find.
Does this survive to the high loop, this conclusion?
Yeah, I didn't check it carefully, but I'm going to say something about that in a moment.
Okay.
However, the nice thing about these guys, I corresponded with Mr. Kudlis, and it turns out that when you find that paper on the archive, not in the journal, but on the archive, they give Mathematica files with all the coefficients. So everyone can pick up those coefficients and play with them, which I did, and I'll tell you in a moment what I found from that. So, so far, I either told you about work of my own some 45 years ago, or I told you of recent work by others about the NC value. And in the next few slides, I will show you some new results that I propose as new directions to go along. My first comment is that physically, n must be equal to d. Remember what n was. N was the number of components of the order parameter. But the number of components of the order parameter is equal to the number of axes of the Euclidean coordinates. So clearly, both should be equal to each other, and that's an important ingredient. In fact, already in 1973, Michael Fisher and I, this was my first article, my first paper on the renormalization group, we worked on the dipole-dipole interactions. And the dipole-dipole interaction involves scalar products of R, the distance between the two spins, and the spin. So clearly, to discuss such a scalar product, you must have the space and the spin to have the same dimension. So R must be, N must be equal to D. In particular, in the last part of the talk, if I get there, we will encounter terms that involve K sum over alpha, K alpha squared, Q alpha squared. These terms represent coupling of the fluctuations, the wave vector of the fluctuations, and the order parameter. In fact, this term indicates that the fluctuations suppose the octahedra rotate around the z-axis. So the fluctuations along the z-axis are much weaker than the fluctuations in the transverse direction. Remember, this oxidant is on both this unit cell and the next unit cell. So the activity of fluctuations in the xy plane when the order parameter is in the z direction are much stronger than the fluctuations along z. In fact, some people at one point thought that maybe the problem even breaks into separate two-dimensional problems because the fluctuations in two dimensions are much stronger than in the third direction. That is reflected by this term in the Hamiltonian, and in the last part of my talk, I will return to that. But anyway, what I want to emphasize is that n must be equal to d must be equal to 4 minus epsilon. So my point is that what we really need to do is to live on the ND plane. N is in that direction, D is in that direction. What people did in the Epsilon expansion so far was to go along this direction. They start in 4 dimensions, but at N equals 3, and they extrapolate like that. Or they did 2 plus epsilon, which I will mention, and then they stopped at D equals 2, N equals 3, and they went that way. Or they did, in fact, I did 1 over N expansion, and then you come down from N equals infinity down to this point. But we want to reach this point, N equals 3 and D equals 3. And what I propose now is that instead of going that way in the epsilon expansion, it's more physical to go that way in the epsilon expansion, because D must be equal to N and both must be equal to 4 minus epsilon. So then I took the NC from the Russian guys that I just showed you. This was on the previous slide. But then I said, let me find out when N, which is 4 minus epsilon, becomes equal to NC. That will give me the value of epsilon along this line where the 2 fixed points coincide, the cubic and the Heisenberg. So I'm going to solve this equation for epsilon going in this direction. And I did this with my colleague Ora Entin-Wollmann. On the first line up there, you see this equation. This must be equal to 0. So this is the equation N equals 4 minus epsilon equals NC of epsilon. So both sides have epsilon, and this is a polynomial in epsilon. I took that polynomial and I padded it. So you see the triangle of Padez, and we are looking for a 0 of this equation. In fact, this plot shows all these Padez as function of epsilon. And what you see is that, and the 0 of this function should give me the critical epsilon where the cubic and the Heisenberg fixed points coincide. And so these are all the Padez. You see some Padez don't have a 0 at all, but we are looking for zeros of this. And you find a function of epsilon, a 0 at 0.22, a 0 at 0.37, a 0 at 0.39, a 0 at 0.9, and only 1 0 at 1.5. So all the zeros from these Padez are below 1. Epsilon below 1 means N and D above 3. This is 4 minus epsilon dimensions. And since these zeros of these Padez are relatively small numbers, you know that the epsilon expansion becomes better and better for smaller and smaller epsilon. So I would argue that this is a better, we should trust these numbers maybe better than the other numbers because they are smaller, and they tell us that the 0 of NC happens at values which are smaller than 1. Therefore, the Heisenberg fixed point should win. However, I did not yet do Padez-Borel on this. I did not yet do the same for other quantities that have to vanish at NC. This is work in progress, and Ora and I will surely continue along this direction and stay tuned to hear more results on that.
Can I ask a question?
Yes.
So I think I understand the calculation you're doing, but I'm not sure I understand why you say Heisenberg should win based on this.
Because is larger than 3, so D equals 3, N equals 3 is below NC.
Yeah, but what is the meaning of NC? NC you said is the point where
the cubic and Heisenberg fixed point coincide. So if I go back to this diagram,
but after they coincided,
we know that up here the cubic fixed point wins. But then we go down, and at some point the Heisenberg and the fixed point coincide, and there below that point it's the Heisenberg fixed point that wins. So we start with the cubic fixed point winning up here. There is a critical value epsilon c somewhere here. And then below that, it's the Heisenberg fixed point that wins, including this point.
Okay, I understand. But this cannot be
That's
true,
the logic.
right?
Now, of course, this is look at this series. The coefficients are growing quickly with the order. It's a bad series. And the fact that I padded it does not necessarily tell me that the answer is correct. And in particular, let me just say, I could obtain this pade not for NC, but I could have asked, when does V of the cubic fixed point vanish? That was Slava's question of a minute ago. And when I do that, I again find that that happens around here, around 0.4, but also there are two values, one slightly below 1 and one slightly above 1, at which some pades vanish. So there are zeros of the pades both far away from 3 dimensions, but also near 3 dimensions, either below or above. So the question is still open, but this is a new way to look at this question.
May I make a comment to that?
Yes.
You can do the epsilon expansion for NC minus D. This is a linear term, and it will not really change the large order behavior, but you have to do this when at 5 loop or 6 loop order, the 6 loop order, you cannot rely on Pade resumization.
I know.
If you do the Pade-Borel on this function, you will get very close, at least, to the result from the Russian group, this 2.915.
I know, but this is doing the Pade-Borel on the right-hand side of the upper line. What I'm doing is something different. I don't Pade the right-hand side. I first equate it to the left-hand side, and then I ask, when will it be 0? So it's a different Pade. You know that if you Pade different expressions, you get different results. It's a different approach to answer the same question, however, looked at from a different point of view.
But Amnon, we could approach that point n equal d equal 3 from an infinite number of different directions.
I know.
So the fact that you said that this direction is more physical, with the fact that you said that this direction more physical is kind of beyond the point. If you think that your Pade method, people who do Pade method, they believe that they have it under control, then I, as a user of this result, I can demand that the result should give the same consistent results from all different directions.
Most probably, when I follow up the approach I just described, doing Pade-Borel to it and Pade-Borel, Leroy, whatever, I may end up with the same conclusion. This is a very preliminary result. However, I am willing to follow you, Slava, and trust the Bootstrap, which does the calculation exactly at that point. And then there is no expansion and no Pade and nothing. And the Bootstrap people, including all the people in the audience, told me that the value of NC at 3 dimensions is above 3. Or in other words, they tell me that when they analyze n equals 3, d equals 3, they find that the Heisenberg fixed point is unstable and the cubic fixed point is stable. Is that fair, Slava?
Yeah, that's correct. Yeah.
So that's it. Now, let me just say that
Sorry, can I also ask a question?
Yes.
Yeah, on your slide with the Pade, the previous slide. Okay, good. Yeah. So you have some Pades that do have a 0 here and some that don't. So assume there is one picture that's the true correct picture, and assume that it doesn't have a 0. What's the interpretation of that?
It doesn't vanish well. No, this quantity must vanish if I had an exact expression for NC as function of dimension. Then I would equate it to the dimension, which is 4 minus epsilon, And it should vanish, it should agree with that, because the physics says that I need the result at n equals d. So all the results should eventually converge to the same answer. The only question is how you get there, and I leave that. This approach is very preliminary, and I'm just telling you about it because we'll continue this, and you will hear about it more.
But some of these curves would imply NC in 3 dimensions is below 3, and some of the curves would imply it's above 3, right? Is that the correct?
No, at the end, the nature has only one answer. Nature either tells us that at n equals d equals 3, the Heisenberg fixed point is stable, or at n equals d equals 3, the cubic fixed point is stable. There is
Well, we know now from the
no discussion that only one of these answers should be correct. The question is, how do we calculate it?
Yeah, we know now from the bootstrap that the Heisenberg is.
I agree, and that's what I said.
Yeah.
So
that would mean
I'll continue under that assumption for the rest of this discussion.
So just to understand this picture, that means that you expect it to be the 0 below 1 in this picture.
Yes. Yes. If I were to do the epsilon expansion along that line, then the 0 should be here if the bootstrap is correct. I find it somewhere. Where is my arrow? I find it somewhere here, and the bootstrap finds it somewhere here.
Oh.
Anyway, let me continue because I have lots of material.
Okay, yeah.
When you increase n, this picture, remember, is a function of n. And when I increase n, the cubic fixed point moves up towards the decoupled Ising fixed point. When I decrease n, it moves down, and at some point it crosses the Heisenberg fixed point. So this picture depends on n. And if n is very, very large, the cubic fixed point is very close to here. When n is infinite, then we need to ask what happens to the Ising fixed point in the presence of the cubic term. And at the time in 1973, many of us worked both on the epsilon expansion and on the 1/n expansion. So 1/n means that we approach our problem from above as function of n. And what I showed in this paper, 1973, is that if you maneuver u and v to leading order in 1/n, then you do find the cubic fixed point and the isotropic fixed point at n equals infinity. And here are the cubic exponents, and here are the Heisenberg exponents at n equals infinity. And at n equals infinity, these exponents are very different from each other. The cubic value for gamma is 1.43 to leading order in 1/n, and the isotropic gamma is equal to 2. Eta is always small, so it is small there and it is 0 there. So this is another direction that people might elaborate. It is interesting that the cubic fixed point has exact values at the limit n goes to infinity, and in fact, its exact values are what is called Fisher renormalized. And I mentioned Fisher renormalization of exponents already before. If you know the isotropic exponents, and if you switch on a coupling which is of the type energy-energy coupling, then you can end up with a renormalization of your exponents such that many exponents get divided by 1 minus alpha. But I have no time, not much more time to go on. The bicritical points were also discussed in the 2 plus epsilon dimension by Pelkovich and Nelson. Pelkovich was a student at Harvard. This is 1976. And they calculated the exponent for V as function of epsilon at fixed n. So they went, in fact, at d equals, at n equals a fixed value, n, say 3, and they went from 2 dimensions upwards along this axis, and they found that lambda v has such an expansion. But notice, as we also saw on many of the slides on the previous talk today, that both the exponents, the stability exponent for quadratic anisotropy is up there somewhere here, and cubic anisotropy, the variable of the expansion is epsilon divided by n minus 2. Epsilon is d minus 2, I remind you. This is the typical expansion variable. So if epsilon is equal to d minus 2, and if d is equal to n is equal to 2 plus epsilon, then n minus 2 is epsilon, and epsilon is up here. Epsilon cancels, and this series is no longer in a small argument. This is n equals 2 in 2 dimensions is a critical value of n. So it is not clear how to extrapolate this expansion from 2 dimensions upwards along this direction, which we want. And in fact, the behavior near the point n equals 2, d equals 2 has been in the literature for a long time. In 1980, Carly and Humber discussed the vicinity of that point and found regions in the ND plane where there may be problems. And here is a paper from the archive of last week, May 11, 2021, by these Polish people. In fact, I wrote to Cardi about his paper, and he said, ignore my paper, is wrong. These Poles have solved the problem better. And these guys of a few weeks ago then discussed what happens around the n equals 2, d equals 2 point, which is the Kosterlitz-Thouless transition. And they found that there is no specific problem when you go along this diagonal line, which is n equals d. The Cardi-Humber line, which was here as a singularity, is not really singular, they say. However, they do not teach us how to go along this line. So this is, again, an open question that I pose to the audience. If anybody can tell me how to do the 2 plus epsilon dimension along this diagonal, I will be grateful. Okay. The next chapter is a visit by this guy in Israel in December 2018. In fact, he visited Barak Kol at the Hebrew University and Ofer Aharony at the Weizmann Institute. Some of you may know these two guys. They are string theorists at the Hebrew University at the Weizmann. And Slava came to see me in Tel Aviv, and he said to me, if the cubic fixed point wins, as the Bootstat community claims, he said, what are the implications for the displaced phase transitions in the perovskites? And since December 2018, Slava and I have corresponded back and forth on this problem. We agreed that we must do something about this, but Slava kept publishing 100-page papers every month, so he was too busy to address this question. However, when he invited me to speak here today, I took the challenge and started thinking again about this question. So from now on, I will assume that the bootstrap people maybe are right, and what are the implications. So let's go back to the beginning of this story. The beginning of this story was this diagram, which, as I told you, has been copied by many people in many papers. And what I did on this slide is only add the initial lanthanum aluminate up here and the initial strontium titanate down here. Remember, the Landau-Ginzburg free energy of lanthanum aluminate has positive V. The initial Landau-Ginzburg theory for strontium titanate has negative V. So initially, lanthanum aluminate is up there and strontium titanate is down here, and then they start flowing according to the renormalization group. And the cubic fixed point is down here on this left side of this diagram, and therefore strontium titanate may be above this line which contains the cubic fixed point. And if that is true, then indeed both strontium titanate and lanthanum aluminate will flow to the Heisenberg fixed point according to this scenario. And this is the scenario that everyone took up until recently. However, the Bootstrap people tell me that the correct picture is this one. Cubic is stable, Heisenberg is unstable, lanthanum aluminate is up there, strontium titanate is down here. Look at this picture. Lanthanum aluminate indeed will flow to the cubic fixed point. However, strontium titanate will never flow to the cubic fixed point because it is down here. And there is a boundary blocking it from flowing up there. V cannot change sign under renormalization group. So what will happen to the strontium titanate initial point is that it may first flow close to the Heisenberg fixed point, because maybe the exponent showing the correction, the Heisenberg exponent is the U is an irrelevant variable near the Heisenberg fixed point. Sorry, I don't see my pointer. Pointer. Okay, so the Heisenberg fixed point is stable under U. So you flow first in that direction, but then there is a line here along which you realize that V is a relevant variable at this fixed point. So you flow away from this point. And if you are down here, you will flow close, but then you will flow that way. Flowing that way means that eventually you cross the line U equals minus V, which is the limit of stability of the Landau theory. And then you will have to add 6 order terms, but then eventually you will become first order. So the universality that we mentioned in the beginning of lanthanum aluminate and strontium titanate is in fact dead by this point of history.
Can I ask a question?
Yes.
So is there any particular reason why you put lanthanum aluminate much further away from the V equals 0 axis?
It's somewhere in that quarter plane.
But in principle, at least for strontium titanate, this question is quite important, whether the initial value of V is small or large.
In fact, the parameters of the Ginzburg-Landau theory, of the Landau theory, were calculated by Cowley, maybe also by Bruce, and there is a lot of literature on what are the real initial values of U and V for strontium titanate. I don't know if they exist for lanthanum aluminate. Alistair, do you know? Alistair Bruce doesn't answer. Maybe he is muted.
Hang on. Hello. Hi, Amnon. I might have known once, but we're talking about 45 years ago.
Right. Even more. You started publishing 50 years ago.
Okay.
Do you know if at that time there were the bare values of U and V for these two materials?
Yeah, well, I think the answer to the question about the sign of V is basically settled by the fact that the low temperature phase of lanthanum aluminate is trigonal and strontium titanate is tetragonal. Those are the kind of simple.
That's obvious, but Slava wants more. He wants to know where exactly is the initial point in this plane.
No, I suspect that's not known. And actually, I think it's largely irrelevant because as you probably will be coming to, I think the bigger issue here is the cubic anisotropy.
Yeah, I'll get there if I have time. I think I have 15 minutes left. So,
I mean, yeah.
Yeah.
Okay.
Anyway, Slava, this is an open question that I leave open today.
Okay,
Next.
thanks.
What is predicted for NC? So as we saw from my history description, and in particular from the Bootstrap results, the cubic fixed point, in fact, is very close to the Heisenberg fixed point. And since the 2 points are very close, the exponents of the flow of V along this blue line, those exponents are very, very small because they are very close to vanishing. If these 2 points were identical, then V would be, the exponent lambda V would be actually 0. So both lanthanum aluminate and strontium titanate would move very slowly in the V direction. So if they move very slowly, that means that you cannot forget about this V, even if it is irrelevant near the cubic fixed point. You must assume there exist effective exponents which are determined by where the initial values of lanthanum aluminate and strontium titanate are concerned. So any value measured in the experiment could be in fact due to the fact that we have not reached the fixed point yet. And therefore, if it does not agree with any fixed point, don't worry about it. There are corrections to scaling around. Furthermore, however, if this is the situation, the cubic fixed point is up there and strontium titanate is down here, then as I already told you, it will first maybe move that way, but then it will move that way, and it will become first order when it crosses the stability line. In fact, rubidium calcium fluoride, as I will mention in a few minutes, actually sits maybe even further down along the V direction, and it does show a first order transition experimentally, maybe because it is close to here and therefore it's very easy for it to flow down there, maybe for other reasons. I'll come there in a moment. However, when we recall this experiment by Miller, which was the first experimental picture I gave in these lectures, remember I emphasized this apparent universality of strontium titanate and lanthanum aluminate. They actually data collapsed on top of each other, both exhibited exactly the same exponent with inaccuracy and so on. And the question I posed at the time is, which universality class is this? For strontium titanate, I already resolved this issue by showing you that in fact beta is not 0.33. 0.33 is an effective exponent due to a crossover from the isotropic behavior to Ising behavior. I am not aware of similar explanations for lanthanum aluminate. I am sure they exist. They must have polished their samples for both of these systems. The EPR results are much better when you have polished samples and therefore uniaxial stress. However, these two materials still look very similar. This would be explained if the Heisenberg fixed point was stable, but if the cubic fixed point is stable, I just told you that no way they do not belong to the same universality class. Next, suppose NC is equal to 3. All the results so far say that NC is very close to 3. If it is actually exactly equal to C, then the cubic fixed point and the Heisenberg fixed point coincide on the U axis. And then we have to solve the recursion relations around this joint fixed point. So if I look at the recursion relation for V, remember that when the two fixed points coincide, the exponent lambda V, which describes the linear flow of V under renormalization, lambda V vanishes. That's the way we identified NC. So the recursion relation for V is really dV dL begins with V squared times the coefficient, which depends on U. For the aficionados, this is the beta function, beta 2, beta V. Beta 2 is a double expansion in U and in V. However, the coefficient of V, which was a polynomial in U, vanished. That's how we found NC. And then this is a polynomial in U, and then you can go to higher order. But if V is very small, we can stop at V squared. And then we need to solve the differential equation dV dL is equal A times V squared. So dV over V squared is A times dL. You can integrate both sides. On the left side, the integral of 1 over V squared is 1 over V minus 1 over V. So you integrate it from 0 to L. Left side becomes this. Right side, just the integral of dL is L. You find that V of L is V of 0 divided by this. So you see it depends on L, not on E to the L, as the others did in all my talk until this point. It is linear in L. But remember, E to the L is psi, so L is the log of psi, which is the log of T. So V actually depends only logarithmically on T minus Tc. This is a very, very slow dependence, and therefore the flow along this line now is very, very, very slow. On a range, when you have maybe 2 orders of magnitude of temperature, of relative temperature, T minus Tc over Tc varies, say, between 100th and 1, you will not even see such a variation. So this will remain constant wherever you started. Furthermore, however, look at this behavior. Suppose A is negative. If A is negative and V is positive, if A is negative, no, forget about it. I don't want to think aloud. Clearly, A has a given sign. You have to calculate it from the recursion relations up here. It's a number. If A has a fixed value and the initial V is positive, let me assume A is negative. If A is negative and, no. Anyway, if you switch the sign of V, you see that for one sign of V, this denominator grows, and for the other sign of V, this denominator decreases. So let's choose the sign of A such that V decreases this way, approaching the cubic equal Heisenberg fixed point, and it increases this way. So this will confirm this picture. To have such a picture in which V approaches this point from this side, but goes away from this point on the other side, we need A to be negative, and I haven't calculated A yet, although the information is available as a series in U, which is a series in epsilon, and you go calculate it. It will suffer from all the Borel extensions and so on. But I still argue that it's calculable in principle. I don't know if the Bootstat people can calculate it for me, but the conclusion is, again, strontium titanate should go first order. Okay. Now I come to the last part of this talk, which will be, I'll have to run through 20 transparencies, but let me just explain to you the logic. In addition to strontium titanate, in which the order parameter is along an axis, namely the transition is from cubic to tetragonal, potassium manganese fluoride and rubidium calcium fluoride and potassium, potassium calcium fluoride all have the same behavior. However, when you repeat the measurements for rubidium calcium fluoride, as these people did in when was this? 1985. They discovered that.
So I'm sorry. All these guys which are on the bottom, they behave exactly like strontium titanate, so they have second.
In the sense of the ordered phase at low temperature. The ordered phase is tetragonal.
Okay. Good. Thanks.
And the rotation of the octahedra is described here the same as in strontium titanate.
Okay.
They rotate counterclockwise and counterclockwise. I don't know if you can see me.
Yeah, I can see you.
I don't see myself. Wait.
Yeah, I can see. Thank you.
Yeah. Oops.
I mean, actually, how much time would you need to go through this, like at the same speed as you went? Because we would like to understand. So
that's fine.
Yeah.
Give me only 3 hours, right?
Okay.
So anyway, the ordered phase is the same. So a priori, rubidium calcium fluoride has the same initial free energy density as strontium titanate does. However, its coefficients U and V are different. And what they observe is a first order transition. You see that it has first deviations from the linear line. So it does show some effective exponents for a range of temperature. But then before you reach the critical point, there is a jump, a first order jump in the order parameter. This has a first order transition. So either it was already, let me go back like this. Either it was already down here, so it was unstable at the Landau level, as many people assumed in the 80s and 90s, or it was here, but then it suffered some renormalization steps, which took it here, and it became strongly first order. So the question is, why did that happen? we need scenarios that turn, sorry, there is an R here, turn second order transitions into first order ones. And of course, there is the trivial explanation. You don't need renormalization group because this jump happens before the correlation length even had a chance to grow very much. So we don't care about fluctuations. Landau theory says first order. However, if Landau theory did not say first order, then we need a fluctuation mechanism that turns the first order transition into a second order transition. And that is the last part of this talk, and I have 4 minutes for that, unless the chairman allows me more time. And I will now run very quickly through several scenarios which generate first order fluctuation-driven first order transition. The first one is by Blankstein, who was a student in Tel Aviv. I cannot see the year. What we did in that paper is add s to the 6. I already told you that s to the 6 is highly irrelevant. And that's why we didn't discuss it up to this point. You look at the recursion relation for U6, and you see it's 6 minus 2d. So in 4 minus epsilon dimensions, this is minus 2. It's highly irrelevant near 4 dimensions. It's marginal in 3 dimensions, but that we'll discuss somewhere else. So it is relevant. However, U6 appears in the recursion relation for U4. So when you start, U6 was not 0. And in the first few iterations, U6 decreases, but at the same time, it influences U4, and it makes it more positive. Okay. So in fact, the U4 scaling variable, you remember I mentioned that we need to linearize the Hamiltonian near the fixed point. The linear variables, which I called mu in my renormalization group chapter, those mu's are linear combinations of the original Hamiltonian variables. And in fact, the scaling variable for u is not the initial u, it's u plus some coefficient times u6. This is the correct scaling variable which will appear as mu in my scaling theory. And when you solve the whole problem using u6 also in the game and allowing it to gradually decrease, treat it as a dangerous irrelevant variable, you discover that in the plane U4, U6, there is a line of first order transitions for the full problem of U4 and U6. However, since U6 initially increases U4, it can turn this first order transition into a second order transition or vice versa. This is a mechanism that uses the renormalization group to change first order transitions into second order transitions. And in fact, for Blankstein and I did at the time was also to ask what happens to the bicritical and tricritical, bicritical and tetracritical phase diagrams. Remember, originally, this was the bicritical diagram and this was the tetracritical diagram, but now we add U6 and U6 shifts the variables and the shift depends on the number of spin components. And then we discovered that the second order transition can become first order for larger anisotropy here or here, or here, the first order transition can become a second order transition as function of anisotropy and so on. All these situations in which tricritical points separating first from second order transitions can arise just because we started in the wrong place in the multi-variable initial Hamiltonian. So this is one scenario. I'm running now very quickly. Here is another scenario in which again, or maybe it's in fact the same scenario in which a second order transition turns first order, and you can look at it in the U6, U4 multi-plane, and let me forget about that. And then we go back to our friends Domani, Mukamel, and Fisher. Domani is visiting Jaffa right now, but Mukamel is in the audience. And remember this phase diagram, which they copied from the previous discussions, but then they went back to the issue of what happens to these bicritical phase diagrams when you go to this UV plane. And then I told you that in this UV plane, you might find yourself, say, in this region. Suppose this was the cubic fixed point, and this was the Heisenberg fixed point, and strontium titanate was here, and you were flowing that way. They calculated actually what happens as function of U and V in these different regions, and they found that indeed the transition can become first order for a while, but then it will become second order again, because the effect of fluctuations is larger for a small anisotropy than for a large anisotropy. This is Ising, and Ising doesn't suffer much, but this is close already to Heisenberg or to cubic, and then it does suffer from these various fluctuations, and you can turn to have tricritical points here, and they discussed this, and we just copied that in the Blankstein following paper. This is again from their paper of Domani, Mukamel, and Fisher. And as you see, what they said, we need, in addition to this scaling field of the anisotropy, there must be this anisotropy. W is now the deviation from the fixed point lines, right? W in the previous slide, W was, for example, here. It is the deviation from this line. Landau theory says second order transition here, but renormalization group, it flows to there and it becomes first order. And they said we must add W, this variable here, as an irrelevant variable, but as an important variable, because for some ranges in the parameter space, you have tricritical points as function of G, and you have first order transition first and second order transitions later. And then these references mention many papers by Mukamel and Krinsky, and Bach, Krinsky and Mukamel and Krinsky, and so on, in which they describe many, many situations in which you find yourself in a region from which you cannot reach any stable fixed point. And this is an issue that Toledano already mentioned. And in all these papers, they discuss what happens when you cannot reach a stable fixed point. And here, this was the simplest example in which it doesn't work. But in these papers, they consider situations in which n, the number of components of the order parameter, becomes larger and larger and larger. So we are far above NC, and above NC, we can have a multitude of fixed points, and many things can happen. In fact, yesterday evening, we also saw some such situations. In fact, I myself, let's see. So, no, this is just a curiosity. When I prepared for this talk, I looked for the cubic fixed point, and then I fell upon this Physrev letter from people in cosmology. And what they said is that there is a new interest in weakly first order transition in cosmology, specifically in the genesis of matter. And they present this Hamiltonian, which I hope you all know and love by now. And then they say that it becomes first order because you are in a region in which this Hamiltonian gives you a first order. So whatever we are discussing here about the perovskites is also relevant for the genesis of matter. But this is just a point of curiosity. And now here are more diagrams that Blankstein and Mukamel found with many, many possible scenarios of second order transitions becoming first order. And this is just to show you that you can generalize the Hamiltonian I just showed you. This is a Hamiltonian in which you have n times m component models. this was discussed yesterday evening also. There is the sum over all the Nm components to the power of 4. This is the isotropic Nm term, but then there is a V, but V now is not a sum over just S alpha one component, but it takes an M component vector and squares it, and then takes the squares that. And then there can be two more types of couplings, quartic couplings. So here we have 1, 2, 3, 4 quartic parameters or quartic Hamiltonians operators in our problem. And in this particular problem, I was interested in the random problem. So in fact, n at the end had to go to 0, but forget the details. I just found 14 fixed points with various stabilities to leading order in epsilon. And there are many more papers in the literature, particularly, as I said, Mukamel and Krinsky, who find fixed points with many, many components. And they all claim that when you are out of the region of attraction, you go first order. Now, I have no time for the last part of the discussion, but let me just, Chairman, do I have a few more minutes? Where is the chairman?
I'm here. I unmute myself. The chairman is pretty lenient, so you can go ahead for a few minutes.
So I will not go to much of the details, but I already explained to you the physics. When we look at the perpendicular direction of the rotation axis, then you have large fluctuations which are represented by a k square. K is what was q up to this point in the plane. However, when you look along the rotation axis, the fluctuations in that direction are much weaker, and therefore there is a new term in the Hamiltonian which says that the coefficient of q square in the plane and perpendicular to the plane, those two coefficients are very different. And this I copied from the Cowley review that I mentioned before about the perovskites. And in fact, experimentally, they said, this is in fact is the soft mode. This is the frequency square of the soft mode we are discussing. They found experimentally F is minus 0.97. So the kz square almost cancels from the kz square here. And this is almost only kx square plus ky square. And therefore, as I said, some people thought this is actually a two-dimensional problem. The planes are decoupled. Right? And in fact, when I studied the dipolar systems, I studied the dipole-dipole interaction systems with both for the ferromagnet and for the antiferromagnet. The ferromagnet has a propagator which is much more complicated, but as I mentioned, we are now discussing an antiferro distortive situation, and therefore the quartic and the cubic terms are similar to what we had before. However, this propagator now, for the case we are discussing, has this new F variable. In fact, it also has a term along a diagonal in the Q space, Q alpha, Q beta. But this F, we were just told, is very close to 0, or F is very close to 1, and that affects the recursion relation. So already in that paper in 1973, I looked at the recursion relations of U and V and F. F is now an important variable in this problem because it also represents cubic symmetry and the breaking of the cubic symmetry by the fluctuations along the order parameter direction. And as you see, you don't need to follow the details of these recursion relations, but F and V are now coupled. F appears in the recursion relation for V, and V appears in the recursion relation for F, and therefore you must really solve all these problems. At the time,
for example, can I ask a question?
Yes.
So the fact that this, we know the initial value of F very well. We don't know initial value of V. I mean, we know that it's...
Slava, we are now talking theory. So
yeah, theory, but I was just wondering, you know, because F is present in the equation for V, you know, can it give V a kick and move it like from the upper, from you, before you said that V cannot cross zero region.
definitely yes.
Okay, because
So
before you said
as
that V cannot cross V
influences
equals
this,
zero.
I am not sure it can move it from the upper plane, half plane to the lower half plane. It can change the value of V.
Okay.
So you have to study these recursion relations in detail. There was not much work done on that. However, I already mentioned Thomas Natterman. Thomas Natterman, at the time, this is 1976, he was isolated in Leipzig, and he worked in parallel on these problems. And he looked at this, and he said, there is F here. Let's do the recursion relations with F. And he actually said that we should solve this with F in our recursion relations. And in fact, this coefficient here appears as the propagator of the recursion relations. It appears in the integrals over Q. The integrals over Q are typically integrals over the Green's function, which is 1 over this. And if there is a singularity because of F, you must worry about it. He calculated these integrals for F close to 1. And indeed, he found that if we keep F in the calculation, we end up with the first order transition. What I did in my paper here was I didn't treat F close to 1. I treated F close to 0 because I did recursion relations near the fixed point of the Heisenberg fixed point, which I assumed at the time is the important fixed point. And therefore, I treated F near 0. He treated F near 1. But anyway, he did that. And then we went to the experiments. Remember these experiments. And no, these are now new experiments. So as a result of this, Miller and Berlinger and these guys repeated the experiments on rubidium calcium fluoride. However, they changed the stress, or changed the the stress on their sample, and in fact they discovered that they can turn the first order transition of rubidium calcium fluoride into a second order transition by changing this stress variable. And as they did that, what they found is that as function of this new variable, they found that there is a tricritical point. At large stress, they reproduce the Ising variable because this is highly uniaxial now. Large stress, this is like strontium titanate, highly stressed. But there is an intermediate point at which beta becomes of the order of 0.18. This is the point at which the transition is just intermediate. This is this line number 2. And then at lower values, they had a first order transition. So this was a paper, November 1978. And joining that paper back to back, November 1978, there was a theory paper by Alistair Bruce and myself. So you see the collaboration and friendship of Bruce and I continued also in 1978. And we said, let's look at this Hamiltonian now, but with the correct F in U2, and let's ask what the consequences of that are, and can we relate to the experiments in the adjoining Fizrev letter by Miller and company. So the U2 in a cubic system, as I just mentioned, has a Q perpendicular, where am I? Pointer. I just, no, pointer, laser pointer, here. I just told you that Q perp, when the order parameter is along alpha, that remains large. However, there is a term with Q parallel square, which is practically 0. So let's forget about Q parallel square, and let's assume that the leading Q parallel is not Q parallel square, but Q parallel to a higher power, maybe 2L. If L is infinite, then it's a two-dimensional problem. but the higher order terms in Q were not measured, and in principle they could be there. Let's assume that the real problem actually has Q square for all the transverse component, but the longitudinal component has Q to the power 2L. This is a problem which has been known as the Lifshitz problem. The Lifshitz problem has been discussed in the literature at length. So I remind you, Lifshitz is just the usual problem, but with a quadratic term which has different fluctuations in the plane and along the axis. And there are epsilon expansions for the critical Lifshitz point and for the tricritical Lifshitz point and for various other Lifshitz situations. The upper critical dimension for the critical Lifshitz point is 5 minus 1 over L. If L is 2, that will become 3. And then you can expand the exponents around that. The tricritical point Lifshitz has an upper critical dimension of 4 minus 1 over L, and you can do epsilon expansion around that. And therefore, you can estimate from this leading order epsilon expansion the critical and the tricritical exponents for the Lifshitz point. And basically, they are roughly near what Miller and Berlinger measured, and that's it. Since 1980, I left this problem. However, this is a list, a partial list of my personal work since 1980. And as you see, there are many perovskites on this list. Let me just mention this guy. This is a paper in 1980 on gadolinium aluminate oxide, which is a uniaxial antiferromagnet. So it has bicritical points. And in fact, Fishman and I at the time predicted that random fields, that a magnetic field on random uniaxial anisotropies is like a random field, and the random field Ising model, you will hear a lot about this afternoon. So it's an exciting problem. And Heini Rohr measured that, the bicritical point in the presence of random fields, and we published this paper. As you know, Heinrich Rohr soon left this problem, went on to invent the tunneling electron microscope and got the Nobel Prize here. So this is my second occasion of publishing a paper with a nice guy who then moves on and gets the Nobel Prize. It happened to me with Miller, it happened to me with Rohr. I think it is a good idea for you guys to collaborate with me. Who knows where you will go. Okay.
Excuse me, Amnon, you might have noticed that the chairman got onto his feet, so it might not be so
That's fine.
intimidating.
This is the list of remaining problems. This is the list of remaining problems. We are still within the discussion time, I think. And you can read this at your free time. This will be on the recorded lecture, and this I'll put the slides on the website of the conference. Let me just then read the last point in this summary. Communications between conformal field theorists, conformal bootstrap people, and condensed matter physics are useful. Let's continue them. Thank you.
Thank you very much, Amnon, for explaining the genesis of the cubic instability and so on. So we are going to run into a solid wall of singularities at 1 o'clock, because otherwise this afternoon session is going to be delayed. Is there a short comment, a question?
Well, I have a question. So I think, Amnon, you have this quite compelling scenario about lanthanum aluminate on one side and strontium titanate on the other side, and then the first order, second order. This all looks very convincing. So do you think we could
did say that they observe a first order transition in strontium titanate? You have to go very close to TC, but people claim that they have seen that.
Okay, excellent. So do you think that we can get hold of some experimentalists who could do something interesting about checking, because you
I'm
have
going to
new
write
predictions
a paper
now.
about this and encourage the experimentalists to join this. Unfortunately, as I told you, Alex Mueller has been absorbed with high temperature TC, and he is 94 years old now. Let him live a long life. Other people are doing EPR on perovskites, and I will certainly try to publish something that will push them to do more experiments. But of course, this applies not only to perovskites, this applies to antiferromagnets, this applies to many other physics. Nature is not isotropic. Nature has cubic anisotropy on many crystals. So to answer your question, Slava, of 3 years ago, yes, there are implications, there are important implications, and I'm grateful to you for leading me back into this old stuff.
Okay, so I think this is a proper place to stop the discussion. So let's stop here and we'll resume at 2 o'clock, I think.
2?
2, yes. So in 1 hour. So have a nice lunch or whatever your time zone is, and see you in an hour.
Are we staying on the same Zoom site?
Excuse me?
In the afternoon, is it the same Zoom or another Zoom?
I believe it might be another one. You should check
another one.
the
Okay,
site.
thank you.